morning, welcome to this lecture on complex variables. So last class we looked at the L-shaped branch cut that was meant as at a research level, not at a classroom level, but still it is very rarely discussed or presented. So I have given hints as to how an L-shaped cut can come. Now today I discuss the last topic in this series, which is inverse Laplace transform. Inverse Laplace transform. Typically, Laplace transforms are used in engineering in solving ODEs and PDEs, and the inverse Laplace transform is used from a set of tables. So we rarely actually compute the inverse Laplace transform, but it turns out that inverse Laplace transform requires contour integration. So I will show you how to get an inverse Laplace transform using contour integration. So just to begin, Laplace transforms, the forward Laplace transform is typically given by capital F. S is the Laplace symbol variable, integral 0 to infinity f of t, which is the time signal, e to the power of minus st dt. Okay. Our systems are causal, they are excited at time t equal to 0, and so this limit is 0 and it goes off to infinity. Okay. Now in a simplistic sense, the Laplace transform will exist if the function f of t, okay, doesn't grow faster than e to the power minus st can bring it down. Okay, e to the power minus st is a decaying type function. So if f of t doesn't grow faster, so much faster that e to the power minus st cannot pull it down, such functions have Laplace transform. And in engineering it is not a very big issue to find such responses. Okay, all our responses finally decay to 0. Now some formal presentation: a function f of t is said to be of exponential order if there exist real constants m and gamma such that f of t amplitude is bounded in this manner, m e to the power gamma t. Okay. E to the power gamma t is an increasing function, rapidly increasing function. So f of t amplitude is bounded in this fashion. Okay. For all, so we will write for all t greater than some t0. Okay. So in this sense, if you look at the following functions, a 3t plus 2, and let us say b is t cube minus sine t, c e to the power 2t plus 1 plus 5t, then d e to the power t square and e t to the power t. If you look at these functions, these three are of exponential order. Okay, it is very easy to find an e to the power t or some gamma t which bounds this function and this function, and of course this function is easily bounded by 3t, but these two are not of exponential order. Okay, they rise much faster than any e to the power gamma t. Suppose f of t is indeed equal to m e to the power gamma t, where gamma is positive real valued then the Laplace transform of m e to the power gamma t is equal to m integral 0 to infinity e to the power minus s minus gamma t dt, which is equal to minus m e to the power minus s minus gamma t by s minus gamma over the limit 0 to infinity. Now at t equal to infinity, the expression will be bounded. The above expression is bounded only if the real part of s minus gamma is positive. Okay, so which means s, the Laplace variable, is must be restricted to the half plane real part of s greater than gamma. Then Laplace transform of m e to the power of gamma t is equal to m by s minus gamma. Okay. Further, let f of t be continuous and of exponential order. That is, magnitude of f of t is less than or equal to m e to the power gamma t for some m and some gamma. Okay, let's say for all t greater than 0. Then the Laplace transform f of s is equal to integral 0 to infinity f of t e to the power of minus st dt exists for real part of s greater than gamma, and we see magnitude of f of s is equal to the magnitude of the integral 0 to infinity f of t e to the power of minus st dt, okay, which is less than equal to the integral 0 to infinity the magnitude of f of t e to the power of minus st dt, okay, which is less than strictly integral 0 to infinity m e to the power gamma t minus st dt, okay, or magnitude of f of s is definitely less than m dash by s, okay, for some m dash and some s. Now the inverse Laplace transform. Inverse Laplace transform. Okay, we use the Cauchy integral formula to write it. Cauchy integral formula, and we write it as f of s is equal to 1 over twice pi I integral a counterclockwise contour f of z dz by z minus s. Okay. Let us remember that f of s, okay, is bounded let me change the page. F of s is bounded okay, and is analytic for real values of s greater than gamma. Now let's use, so we are going to look at that integral, and let us use the following contour. The contour is this. We have the complex plane, okay, and we have gamma over here. Here is my gamma. So I take a contour counterclockwise, so I come down, okay, from infinity above to infinity below. I go around this infinite semicircle. Okay. Okay. Now, so let me remind you that what we wrote was f of s is equal to 1 over twice pi I integral counterclockwise, okay, counterclockwise f of z dz by z minus s. Okay. Now we switch it to clockwise and change the sign. So f of s is equal to 1 over twice pi I. We switch it to clockwise f of z dz over s minus z. So we brought in two negatives. We change the direction and we change the sign on here. Okay. Now f of z is the Laplace transform. F of z is the Laplace transform. Okay. And decays as bounded by m dash over magnitude of z as before, and as z tends to infinity over a radius r, okay, z tends to infinity over a radius r, the integrand decays. Okay. So integrand here is f of z by s minus z. Okay. F of z is bounded by m dash over r e to the power of I theta. Okay. Then s minus z, okay, s is less important as z tends to infinity. So I have r e to the power of I theta, and then dz is r I e to the power of I theta d theta. So we are essentially looking at the integrand over this semicircle. Okay. So z is parameterized at r e to the power I theta. Okay. So now the magnitude of this f of z dz should be here, f of z dz by s minus z, okay, behaves as m over r 1 by r and r d theta, which tends to 0 as r tends to infinity. Okay. So on this contour, this portion of the integral will not survive. On this contour here, okay, this portion of the integral will not survive. That is what we have shown. Okay. On this semicircular contour, z is equal to r e to the power I theta. So this integrand goes to 0. Okay. So now we are left with we are left with the straight line portion. Okay, so which is what? F of s is equal to 1 over twice pi I. Okay, we are to the right of gamma over here. This is the straight line, so we will write that as sum c minus I infinity to c plus I infinity f of z dz over s minus z. Okay, I will write this again here. Okay, so what we have is f of s is equal to 1 over twice pi I integral the straight line portion c minus I infinity to c plus I infinity f of z dz by s minus z. Now let us take the Laplace inverse. Laplace inverse of this, because it has arisen from a time function. Okay, so now the f of t, which is Laplace inverse of f of s, is equal to 1 over twice pi I, the Laplace inverse c minus I infinity to c plus I infinity f of z dz by s minus z. Okay, now Laplace inverse will act only on s, okay, and not on z. So what we have here is 1 over twice pi I integral c minus I infinity to c plus I infinity. F of z is unaffected, then the Laplace inverse goes and operates on 1 over s minus z. Okay, we can compute the basic Laplace transform of this function e to the power zt, and the Laplace transform of this is 1 over s minus z. Okay, normally we are used to seeing alpha over here, okay, if you remember your Laplace transforms. Okay, so now the Laplace inverse of this is e to the power zt. So we get 1 over twice pi I integral c minus I infinity to c plus I infinity f of z e to the power zt dz, or using another dummy variable 1 over twice pi I, the same integral c minus I infinity to c plus I infinity f of s e to the power st ds. So that is how the Laplace inverse is computed. Okay, actually over a straight line segment where f of s is analytic, the straight line segment going from minus I infinity to plus I infinity. Okay, and this is called the Bromwich integral. This is called the Bromwich integral. Okay, Now let us see. Now let us take an example. Okay. The example is this. Suppose I have, so let us take an example. Okay. The example is this: f of s is equal to 1 over s minus 2 whole squared. Okay. Those of you who remember your Laplace tables may immediately know what f of t is. Okay. So now here I have a pole at s equal to 2. So now we said that f of s is analytic in the region whereas s is greater than some gamma. So you can see that s equal to 2 will be our gamma here. Okay, this is s equal to 2. Okay, and so now we have a straight line segment that goes from this way upwards. Okay. So now we have to compute this integral f of t is equal to 1 over twice pi I integral c minus I infinity to c plus I infinity, which is this line. Okay, e to the power st ds over s minus 2 whole squared. Okay. Now using contour integration, we have to use contour integration. Okay, that is the whole thesis of this series of lectures. We are going to use contour integration. Okay, and again as before, this segment which we want, we do not touch. So we will use principles of contour integration and if possible Cauchy residue theorem, okay, and compute this integral without touching it. Okay. So now what we do, we close this, we close this in the left half plane of the we close it in the left half complex plane. So we now have a closed contour. Okay. So that now the function f of s encloses all its singularities. F of s encloses all its singularities. Encloses all singularities. Now one important point here which I will briefly mention is that in the beginning we said that f of s exists and is analytic to the right of a certain region. To the right of a certain region. So we should ideally sit only in that region and not extend it to the left. Okay. But here is an idea called analytic continuation. Analytic continuation, which is used. Okay. I will explain it using a simple example. Suppose we have this geometric series 1 plus z square and so forth and goes off to infinity. The sum we know is 1 over 1 minus z, okay, provided that magnitude of z is less than 1. Okay, that means what? In the complex plane you have a unit circle, and so you have to be inside the unit circle. so that you have convergence. Okay. However, separate from this idea where we sum this geometric series, there exists a function 1 over z minus 1 or 1 minus z, okay, which is singular only at z equal to 1 and is well behaved everywhere else. There exists a function like that. Okay. Now, the idea of analytic continuation says that this 1 over 1 minus z and this 1 over 1 minus z are identical. They are identical, they are not two separate functions. So, that is the idea of analytic continuation. So, now this function which is supposed to converge inside the z equal to 1 radius extends, okay, and is singular only at z equal to 1. Okay. So, that is the idea of analytic continuation. Now, we are going to do this contour integral, and as before make sure that the function or the integrand goes to 0 on this arc. Okay. We will make sure of that and use the residue theorem. Right now time is running out, so we will continue in the next class. Thank you.